Next week, June 7th. We're going to have online class. So I'm going to upload YouTube, my class in YouTube, so you can check. One 10, I think. 2023. So next week we will have an online class, and I'm going to post it on the YouTube. And you can check like if you like. So previously, we just started learning higher order linear differential equations in the form of an blah 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 a0y is equal to 0. So particularly this equation is called linear ordinary. Actually, because on the right side is 0, we say homogeneous. Ordinary differential equation with constant coefficient. Linear means if y1, y2, yn is the solution of equation 1, then c1y1, c2y2, cnyn is also a solution. That's what linear means, linearity. So sometimes it is convenient to introduce a new operation. And we call this linear differential operator. Differential operator. So operator is a mathematical operation. L some function into new function over 0. In this case, f dash includes 0. Then L y is defined as an dxn dn y an minus 1 dxn minus 1 dn minus 1 y plus a0 y and happen to be 0, right? Since we are solving this equation, in particular, we set L is equal to 0. So that is the linear homogeneous ordinary differential equation with a constant coefficient. Then the linearity means if L y1, y2, yn is equal to 0, then L c1, y1, c2, y2, cn, yn is equal to 0. That's what linearity means. So when when the coefficient an minus 1, a0 are constant, we can actually you can find a solution very easily using the characteristic equations. So for constant coefficient, we can try exponential lambda x as a trial solution. So txt exponential lambda x, lambda exponential lambda x, right? Tx square exponential lambda x is lambda square exponential lambda x, etc., etc. Txn, tn exponential lambda x, lambda to the n exponential lambda x. Then, what happens to this linear operator with lambda x? Simply an lambda n, right? Plus an minus 1 lambda n minus 1. A0 exponential lambda x is equal to 0. So we have an lambda n plus an minus 1 lambda n minus 1 a0 is equal to 0. And this equation is called characteristic equation. to 0, right? You can factorize, sorry. So you can factorize, and then lambda is lambda 1, lambda 2, lambda n. The solution can be so we have the following solution. We can have y1 exponential lambda 1x, y2 exponential lambda 2x, yn exponential lambda nx. Let's consider the case first when all roots are different. So how many of you are taking electric circuit? 전기회로? So you're probably learning about simple differential equation, right? Or probably have learned or learning, either way. Right? So, for example, the typical this problem. So you have like a dx squared 3 dx dy plus 2 y is equal to 0, right? Something like this. Of course, in electric circuit, they usually use t instead of x. So sometimes t is used instead of x. But it doesn't matter. X or t are just independent variables. You can use any variable you want. So for trial solution, we can check exponential lambda x, then lambda squared plus 3 lambda plus 2 is equal to 0, or lambda plus 1, lambda plus 2 is equal to 0. So lambda is either minus 1 or minus 2, right? So we can have two solutions, y1 exponential minus x, y2 exponential minus 2x. And general solution is linear combination of these two. So y c1 exponential minus x, c2 exponential minus 2x. And electric circuit, usually we have two conditions, initial conditions, right? So say y0 is 0, and dx dy 0 is 0, say. In that case, I mean, these initial conditions are arbitrary, so you can set any numbers. So these are initial conditions. Sometimes it's called the von Neumann condition. Same. let's go back to the y1. So y is c1 exponential minus x c2 exponential minus 2x. y0 c1 plus c2 is equal to 0, right? dx dy minus c1 exponential minus x minus 2c2 exponential minus 2x. So dx dy x equal to 0 is minus c1 minus 2c2 is equal to 0, right? So that is c1 plus c2 is equal to 0. c1 plus 2c2 is equal to 0. So in this case, not very interesting because actually all the solutions c1 and c2 is equal to 0. So maybe you can modify what if dx dy x0 is equal to 1? Then maybe a little bit more interesting. In that case, c1 plus c2 is 0, minus c1 minus c2 is equal to 1. So minus the c2 is equal to 1, c2 is minus 1, c1 is equal to 1, right? So in this case, we have a general solution. Y is equal to exponential minus x minus exponential minus 2x. So let's go back to the operator representation. So we have a linear operator, and we have trial solution. This is A0 lambda n, an minus 1, A0 exponential lambda x and actually we call this some characteristic equation. So this is characteristic. If we substitute lambda as lambda 1, then we can have what we have is equal to 0, right? Lambda 2 also equal to 0, right? Lambda n is equal to 0. So when all roots are different, so that means when all root lambda 1, lambda 2, lambda n are different, we have n independent solutions. What if we have a double root? Some of the roots have same value. In that case, or triple root. What if we have the case of a double root? Say C lambda is A, and say lambda minus lambda 1 square, lambda minus lambda 3, lambda minus lambda n exponential lambda x. Oh, no. C is this, right? So say C lambda 1 is equal to 0, right? What about partial lambda 1, partial C lambda? Sorry. D lambda, D, C lambda. What do we have? A twice of an lambda minus lambda 1, lambda minus lambda 3, lambda minus lambda n, right? Plus an lambda minus lambda 1 square, lambda minus lambda 4, lambda minus lambda n, blah, 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 an lambda minus lambda 1 square, lambda minus lambda 3, lambda minus lambda n minus 1. However, if we substitute lambda as lambda 1, what do we get? Here, this is characteristic equation. If we substitute lambda by lambda 1, obviously this is 0, right? If we differentiate this by lambda, we have n different terms. If we substitute lambda by lambda 1, what do we get? This one? 0, right? This one 0. So we obtain d lambda d, c lambda 1 is equal to 0, right? So if you go back to the original equation, so I will just have time to let you copy. So we have set a differential operator. When you substitute lambda as a lambda 1, this is 0. So both, when you substitute lambda 1 to c lambda, it is 0. But also if you substitute lambda 1 to d lambda, d c lambda, it's again 0, right? So, oh, I made a mistake again. We have a paste. Okay. What about if we take derivative d lambda d L that is d lambda d c lambda exponential lambda x plus c lambda lambda exponential lambda x. What if you substitute lambda as lambda 1? As you can see previous, that means this is 0 and this is 0, right? So the whole thing is 0. Or L as an txn tn an minus 1 txn minus 1 tn minus 1 plus blah 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 plus a0. Then L exponential lambda x is what? We have an lambda n an minus 1 lambda n minus 1 a0 exponential lambda x c lambda exponential lambda x, right? And if we substitute exponential lambda x, lambda equal lambda 1, the same as c lambda, but this is 0, right? From our previous empty blank. Okay. Oh. Copy. Okay. I think I have to delete everything. So we have, if summarize our result, equal to 0, right? That means exponential lambda 1x is the solution. Also, d lambda dl equal to 0. But because L is a linear operator, d lambda dl, you can put T lambda T y T lambda T T lambda dy, right? So actually, we can interchange each other. We can change this. We can change the order. So it becomes an tx n minus 1 t n t lambda dy an minus 1 tx n minus 1 t n minus 1 t lambda dy a0 t lambda dy. So we can actually write down as L T lambda dy. So we have very interesting result. So if I think probably you need to copy. This part is maybe conceptually a little bit difficult to understand, but so if L lambda x is given by a n lambda 1 lambda minus lambda 1 square lambda minus lambda 3 lambda minus lambda n exponential lambda x and this gives L lambda x lambda equal lambda 1 is equal to 0, right? So exponential lambda 1x is the solution. But also T lambda dl, and we know now that we can this T lambda d can be put into L. Is equal to 0, right? But T lambda T exponential lambda x equal x exponential lambda x. So if exponential lambda 1 x is a solution, so is x exponential lambda 1 x. So special case. So this part may be a bit boring, but it's a very important topic because in many differential equations you can have a double root. For example, we have a dx square d square y twice of dx dy y is equal to 0. Lambda x lambda square plus 2 lambda plus y not y plus 1 x is 0. So lambda plus 1 square is 0. So lambda is equal to minus 1 minus 1. We have double root. So we know that exponential minus x is a solution. But from previous result, we can have d lambda d exponential lambda x is also solution, right? X exponential minus x is also a solution, right? But let's check. Let's check y2 as x exponential minus x. And let's substitute back into the original equation, and it is 0. So let's check. dx dy2 is exponential minus x exponential minus x, right? If we differentiate this first term, dx square minus exponential minus x minus exponential minus x plus x exponential minus x. X exponential minus x minus 2 exponential minus x, right? So let's see dx square d square y2 plus 2 dx dy2 plus y2 is equal to x exponential minus x minus twice of exponential minus x plus twice of exponential minus x minus twice x exponential minus x plus x exponential minus x. So this cancels each other, and this cancels each other. So this is equal to 0. So y2 is a solution, as expected. How about triple root? Triple root say lambda minus 1 cube exponential lambda x L, say L y. Oh, exponential. Sorry. L lambda x. So obviously, lambda equals to 1 is 0, right? How about if you differentiate once? If we differentiate once, then we have 3 times lambda 1 square exponential lambda x plus lambda 1 cube exponential lambda x. So obviously it's again 0, right? This is same as L actually d lambda d exponential lambda x. If we differentiate twice, six times lambda minus 1 exponential lambda x, lambda minus lambda 3 times 2 exponential lambda x plus 3 lambda minus 1 square exponential lambda x lambda, oh, it should be lambda, plus differentiate lambda. So this is a bit more complicated. Plus 6 lambda if we differentiate this, we have lambda, right? 3 lambda x plus lambda minus lambda cube exponential lambda x plus lambda square lambda minus 1 cube exponential lambda x. Oh. This is a bit more complicated, but if we substitute lambda equal lambda 1 is 0 again. So that means d lambda d exponential lambda x and d lambda square d square exponential lambda x lambda equal lambda 1 are solutions. So this finding the solution for double root, triple root would be very interesting. And I think for this semester, you only need to know up to triple root. So by the way, 21st is a good time for your final exam? No? 21? Or if you like, we can maybe have a bit earlier. 14? Officially, class is supposed to be until 21. So officially class is until 21, but if you like, we can maybe have one week earlier or 1 week later. Oh, you can 안 되지. 기말 성적이 6월 말까지지. I think officially we can take a final exam 21. Let me see. But if you prefer, we can have a week earlier. It's up to you. There's a con and pro. Con of the drawback of taking a final on 14 is next week we are going to have online class, so you don't have a time, you don't have a chance to review. So if you have a 21, you can have more time to talk. 네? 그게 좋죠. So 14, you can have, I think take a final on 14th, but it's after the last class is supposed to be online, so you don't have a time to, I don't have a time to review the whole semester. And 21, maybe 14th, you can, yes. 세 번째 퀴즈는 없을 것 같아요. Yeah, we don't have a time. If you like a third quiz, maybe you can have a 14. Maybe 1 hour quiz and next week final, but so there are cons and pros of taking. So I just want to ask your opinion. 21, raise your hand. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 8, 14. 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 29, 30, 31, 32, 33. Wow. 27. It's closed, so maybe you should take a vote again. Okay. There is one major weakness of drawback or con of taking final 14 because next week I'm going to have online class, so you don't have a time to whole class reviewed by me. Just for you have to after the online class you have to go for final exam. If you take a final on 21, then at least we have a week to review and discuss and all sorts of things for final. And the vote is closed. Just one more time. So I told you about good side and bad side of today, right? So it's supposed to be fair. So this time I will ask you the other way around. 14, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9. Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh. 21. Okay, majority. So final. I asked 14 first. I changed the order. I told you. So example, so if we try our solution is this, we have a lambda cube, 3 lambda square, 3 lambda plus minus lambda minus 1 is equal to 0, or lambda minus 1 to the cube is equal to 0. So exponential x, x exponential x, x squared exponential x are all solutions. So perhaps you can take a break for a few minutes and continue. June 21, 3 hours. You can prepare 3 pages of cheating sheet. So 3 pages, you can actually write down a lot of things, right? This is different case. Another example. So characteristic equations. Try exponential lambda x. What do we have? Lambda square plus 1 is equal to 0. So lambda square is minus 1. A very strange number, right? Lambda is square root of minus 1. We define as I. Imaginary number. Then trial solution is very strange form. So we have a quandary or question. So what is the exponential function is the imaginary exponent. There is a very interesting formula called Euler's formula. Cosine x plus I sine x. No R. Cosine x minus I sine x. 18th century Swiss mathematician, let me check. Euler. Leonhard Euler. It was 1707, 1783. He's a Swiss mathematician. When I was your age, that is about a long time ago. So if I wanted to find the information about Euler, I have to go to the library and check out the Encyclopedia Britannica and search. That was about 30, 40 years ago. But these days, you can check all the information with a cellular phone, right? So there's a big change. So let's see. Let's check the formula. I is square root of minus 1. So I square is minus 1. I cube is minus 1 times I is minus I. I to the 4 is minus I times I is 1. I to the 5th is my I again. So Taylor's expansion we can have exponential ix as a 1 plus ix plus 2 factorial of ix square, 3 factorial ix cube, 4 factorial ix to the 4, 5 factorial ix to the 5, etc., etc. So it's 1 plus ix. I to the square is minus 1, so it is minus 2 factorial of x square, minus I to the 3 factorial of x to the 3, plus x to the 4 divided by 4 factorial, plus I to the x to the 5th x factorial. So we can put together terms, the real part and the imaginary part together. 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, etc., etc., plus I, x minus x to the 3 over 3 factorial plus x to the 5 divided by 5 factorial minus, etc. This formula may be familiar to you, right? This one is a Taylor expansion over cosine x. This is a Taylor expansion over sine x. So Euler's formula is very interesting. So exponential ix cosine x plus I sine x. This Euler's formula was very important because it describes wave. So wave is something that propagates periodically. And this Euler's formula is written by cosine and sine. This is periodic function. So this exponential omega t minus kx describes wave in general. Especially light, electromagnetic wave, too. According to some very famous book with a history of several thousand years, begins with one sentence. There was a light in the beginning. I didn't say the title, but it's a very famous book written by Moses, supposed to be 13th century BC. But if he knew the mathematics, modern mathematics, he probably have written down as there was a Euler's formula in the beginning, instead of saying light, because light exists because of this formula. So our universe is actually, I don't know, was created with a structure, space-time structure such that Euler's formula is true. So this is very important formula and then subject for the next semester. But I think I was like sidetracked. So exponential ix, exponential minus ix is a solution. But this exponential function is difficult to handle. So we can actually say cosine x, sine x as a solution. So for these differential equations, C1 cosine x, C2 sine x. So we can actually apply boundary conditions. In many cases, y0 is 0, say y pi is 1. Let's say 2 over pi. Then this is boundary condition or Dirichlet condition. Anyway, so y0 is sine 0 is 0, so this C1 is equal to 0. Y pi over 2, C2 is equal to 1. In this case, we have a solution that is just sine x. Yx is sine x. And if we have both real and imaginary roots, then another case. Some of you might still need time to copy. Am I going too fast? It's okay. Too slow? Okay, so neither fast nor slow. But another example, dx squared d squared y plus 2 dx dy plus 2y is equal to 0. So characteristic equation, we try lambda x. Lambda squared plus 2 lambda plus 2 is 0. Or lambda plus 1 squared plus 1 is 0, right? So lambda is minus 1 plus minus I. So in this case, y1 is exponential minus x, we can say cosine x. y2 exponential minus x sine x. And you can have either initial condition or boundary condition depending on your taste or depending on the case for the problem. So we have covered enough for the constant coefficient case. Another interesting case is the following. an x to the n y a n minus 1 x n minus 1 dx n minus 1 t n minus 1 a is 0, y is equal to 0. This case is called equidimensional. Dimensional ordinary differential equation. So we make some transformation. In this case, if you didn't use time to copy, then you try yx as a y to the zx. So we assume that, okay, in this case, dx dy is dz dy dx dz, right? Chain rule. If we set z as log x, then dx dz is 1 over x, right? So dx dy is x 1 over x dz dy. Or x dx dy is dz dy. How about second order derivative? Dx squared d squared y is minus 1 over x squared dz dy, right? I mean, we differentiate by x first, then we have minus 1 over x squared plus dx t 1 over x dz dy. It can be written as 1 over x squared dz dy plus 1 over x dz d dz dy dx dz. This is minus 1 over x squared dz dy 1 over x squared dz squared d squared y. Or x squared dx squared d squared y is minus dz dy plus dz d dz dy. You can put dz d dz d minus 1y. Okay? So let's say summarize. X dx dy is dz dy, right? Z was log x. X squared dz dx squared d squared y dz d dz d minus 1 y. If we continue, x to the n dxn dny dz d dz d minus 1 dz d minus 2 dz d minus n plus 1 y. So the original differential equation, so maybe you can have homework. X to the cube maybe you need to, this is homework, you can check. Do one more time, right? You can have one more step. I already have shown up to second order. Just try once more. So maybe you can take 10 minutes at your home. So maybe you can, you can check this during the break time for your favorite weekend drama, such as, I don't know, what is the popular drama these days? 차정숙? No. Actually, my favorite was 슬기로운 의사생활. That was my favorite. And usually they have a 5 to 10 minutes break for commercial. You can check this formula. So the original differential equation A and xn dxn dny plus an minus 1 n minus 1 dxn minus 1 y plus blah 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 a0y is actually an dz dz d minus 1 dz d minus n plus 1 y plus an minus 1 dz minus n plus 2y blah 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 a0y. So we can actually right? If you expand all these terms and then put them together, then we derive equations with different coefficients. To 0. So in this case, trial solution can be what? Exponential lambda z, right? Lambda log x. And this is the same as x to the lambda, right? This is your trial solution. So let's do some example. Say a dx dxy dy is equal to 0. This transform into what? dz d minus 1 to the y, right? Plus a dz dy equal to 0, or dz square d square y a minus 1 dz dy is equal to 0. So let's try. Say if a is 4, b is 3, what do we have? 2. Then we have dz square d square y plus 3 dz dy plus 2y is equal to 0. Then trial solution is lambda z. Then lambda square plus 3 lambda plus 2 y is equal to 0. 2 exponential actually. Exponential lambda z is 0. So lambda plus 1, lambda plus 2 is equal to 0. Lambda equal to minus 1. Lambda equal to minus 2, right? So general solution is y is c1 exponential minus log x, c2 exponential minus 2 log x, c1 x to the minus 1 to the c2 x to the minus 2. That's your general solution. What about double root? Double root is simple, right? Then previously exponential lambda 1z is a solution, right? Then d lambda lambda d exponential lambda z is also solution, right? So that is z exponential lambda 1z log x exponential lambda 1 log x log x to the lambda 1 is also a solution. So let's consider the case of say x squared dx squared d square y plus 3 times dx dy plus y is equal to 0. Then dz d minus ly 3 dz dy plus y is equal to 0, right? So dz squared d square y plus 2 dz dy plus y is equal to 0. So lambda plus 1 square is 0. Lambda equal minus 1. In this case, obviously y1 is exponential minus log x, right? X to the minus 1. y2 log x exponential minus log x. Log x exponential x to the minus 1 is the solution. So let's see. General solution is y is x to the minus 1 plus c1 c2 log x to the minus 1. Consider interesting case. Perhaps boundary condition or initial condition, boundary condition. Either way, 1. y1 is 1. dx dy 1 is okay. I don't like to take a derivative. Say y2. y2 say 0. Then y1 is what? c1 and log 1 is 0, right? Is equal to 1. c1 is equal to 1. y2 c1 over 2 plus c2 log 2 over 2 is equal to 0. So c1 plus c2 log 2 is equal to 0. c1 is 1. So c2 is minus 1 over log 2. Okay? So general solution is yx is x to the minus 1 minus log 2 log x to the minus 1. That's your solution. So another interesting case. X square dx square d square y plus x dx dy plus y is equal to 0. So dz d minus 1 y dz dy plus y is equal to 0. dz square d square y plus y is equal to 0. So trial solution, we can take a trial solution as exponential lambda z. Lambda square plus 1 is 0. Lambda is plus minus I, right? So, very interesting case. We have exponential I z I log x. So this is cosine log x I sine log x. The general solution we can take as y1 simply cosine log x plus y2 sine log x. So it's more convenient than exponential I log x minus I log x. So you can use this as a solution. So we have pretty much covered the homogeneous nth order differential equations with the constant coefficient, and secondarily, equidimensional case. These two are probably the most useful examples for your case. Of course, there are many different kinds of differential equations, infinite number of differential equations, but for you, these two are probably most useful for your forthcoming classes for your junior, senior classes. If you have more difficult cases, then you can learn at graduate level. Next topic is inhomogeneous case. So G and G NUS or the inhomogeneous and inhomogeneous G NUS. That is of second order. So we have Px, Qx, Rx, Y, Sx. So this is a topic maybe we can leave this topic for next week. It seems to be a bit bored, I think. we covered too many cases already. So I think we can stop here today, and next week I'm going to put on my class on the YouTube, and 14th we are going to have there's a last class, and 21st we are going to have a final. I was planning to have 3 quiz, but apparently I didn't fill my quota yet, so